Hi there, Mr. Holcomb here with another episode of The Math Behind the Modules. Okay, I'm trying something new here. We're into the new topic D, and I've added my video here. So now you can see me talking while we're doing this math. Okay, so here we go. Is there anybody out there? All right, here we go. Lesson 22, Congruence Criteria for Triangles SAS. Classwork opening exercise. Answer the following question, then discuss your answer with a partner. Do you think it is possible to know whether there is a rigid motion that takes one triangle to another without actually showing the particular rigid motion? Why or why not? Okay, so answer that question. If you're in a classroom setting, it says do that and then discuss with a partner. And this discussion that follows is going to explain that question or possibly even answer it. All right, so here we go. It is true that we do not need to show the rigid motion to be able to know that there is one. So there's your answer. It is true. Okay. We are going to show that there are criteria that refer to a few parts of the two triangles and a correspondence between them that guarantee congruency, i.e. existence of rigid motion. We start with the side angle side, SAS criteria. Side angle side triangle congruence criteria, SAS, given two triangles ABC and triangle A prime, B prime, C prime. So that side AB equals side A prime, B prime. And as you can see, AB has one mark here. A prime, B prime has one mark there, so they're congruent. The measure of angle A is equal to the measure of angle A prime. There it is, marked with one arc. And AC, side AC, has two marks on it, and side A prime, C prime has two marks on it. So this is how you mark up a diagram's congruency, and you should have learned that in 8th grade. And then the triangles are congruent because of side angle side, and that is called an included side. So just keep in mind that if I had this side and this side, but this angle over here, that is not side angle side, that is angle side angle if I had two angles and a side, or if this angle wasn't here, that'd be side side angle and so on. So we need the angle to be the angle that forms, or that's formed by the two sides that are congruent to the other triangle. So it's the included angle. So the steps below show the most general case for determining a congruence between two triangles that satisfies the SAS criteria. Note that not all steps are needed for every pair of triangles. For example, sometimes the triangles already share a vertex. Sometimes a reflection is needed, sometimes not. It is important to understand that we can always use some or all of the steps below to determine a congruence between the two triangles that satisfy the SAS criteria. So the proof says, provided the two distinct triangles below assume AB equals A prime, B prime, that's a side. The measure of angle A equals the measure of angle A prime, there's your angle included, and AC equals A prime, C prime, another side. Okay, here's page 2, and it says, by our definition of congruence, we have to find a composition of rigid motions that map triangle A prime, B prime, C prime to triangle ABC. We must find a congruence F, so that F of triangle A prime, B prime, C prime equals triangle ABC. First, use a translation T to map a common vertex. Which 2 points determine the appropriate vector? So as you see down here, there is a vector. It starts here, that is called the initial point, and this is the terminal point where it ends, starting and ending. So you start with the starting. So the 2 points we're using are A prime and A. Can any other pair of points be used? Why or why not? Okay, so the answer to that is no. And the reason is, if I mapped this vector here, C prime to C, we're mapping two angles that we do not know are congruent. we were told to assume angle A prime is congruent to angle A. So you always map the congruent part to the congruent part. So let me slide the answer over here so you can copy that. So no, we use A prime and A because only these angles are congruent by assumption. Okay, moving on. State the vector in the picture below that can be used to translate triangle A prime, B prime, C prime. So again, we start with the initial point, the point of that does not have the arrow. And then we go to the terminal end, which is the point, the end that has the arrow. So it's A prime A, and then you put an arrow over top. So there it is. So it is vector A prime A. Using a dotted line, draw an intermediate position of triangle A prime, B prime, C prime as it's moving along the vector. So I've already done that with my program. The best way for you to do this would probably either to be using patty paper, or if you want to be accurate, you'd have to use a calculator, a compass, and a protractor. But I am just going to move this. I've already made it. So if you use patty paper, all they wanted you to do is to create a copy of that triangle showing that it is moving along that vector. So this would be like in motion, that's where it's going. Okay. And then after the translation below, T mapping A prime onto A, triangle A prime, B prime, B, or A prime, B prime, C prime shares one vertex with triangle ABC, and that is A. So as you can see, A prime came along this vector until it got to A. So now the point at this vertex is at this vertex. So now A prime and A are sharing this common point. That's what that is saying. So in fact, we can say that the transformation of A prime A of triangle, and we moved triangle A prime, B prime, C prime to triangle ABC. So that transformation of A prime, B prime, C prime equals triangle ABC. Okay. But it's not ABC yet because it's not right where the other one is. So this is really the transformation of A prime, B prime, C prime to the triangle A, B double prime, C double prime. Okay. Now it says, use a clockwise rotation, capital R, sub angle CAC double prime. So we're going to use a clockwise rotation of the angle CAC double prime. So we're just telling people to take this triangle and rotate it this angle distance to bring side A C double prime to side A C. Or we could go counterclockwise in the opposite direction. We could go this way, mapping A B double prime onto A B. All right, but they're showing the first, so let's go with that. Okay, page 3 brings us to continuing this problem, and it says a rotation of appropriate measure maps A C double prime to A C. They have a little arrow up there. That is saying it's a ray or a vector. It is not. That should just be a segment. I wish I could erase. That should be a segment. It's AC, segment AC prime to AC, segment AC. But how can we be sure that vertex C prime maps to C? Recall that part of our assumption is that the lengths of the sides in question are equal, ensuring that the rotation maps C prime to C. So that's how come we can say that. See the double marks there? So if I went back to the prior page, see how they're congruent? Well, if you are sharing this point and you rotate something that's congruent onto the other, then the lengths will be equal. Therefore, C prime will land right on C. Okay, so that's how we know that they are equal. Now AC equals AC double prime. The translation performed is a rigid motion and thereby did not alter the lengths when AC prime became AC double prime. After the rotation, capital R, of angle CAC double prime, triangle AB prime, B double prime, C double prime, a total of 2 vertices are shared with triangle ABC. Now we have angle A and A double prime sharing A, and C double prime sharing C. Therefore, finally, if B triple prime and B are on opposite sides of the line that join AC, a reflection R across AC brings B double prime onto B. Okay. And we didn't answer this, by the way. It says after the rotation, a total of 2 vertices are shared with triangle ABC, A and C. Therefore, what? I didn't answer that because now it says finally if. So now we can say the rotation of this angle CAC double prime of triangle AB double prime C double prime is going to equal triangle A, now we're looking down here, B triple prime. So every time we do a transformation, the angle or side that is left behind that has not had any changes done to it or shared another vertex, if you will, a prime gets added. That's why we went from A or B to B prime to B triple, double prime to B triple prime. So the rotation of angle CAC of triangle AB double prime C double prime is going to become triangle A B triple prime C. Okay, and then finally, the reflection. Since a reflection is a rigid motion and it preserves angle measures, we know that the measure of angle B triple prime AC, so that's saying here to here to here, this angle here equals the measure of angle B AC. I went the wrong side. Let's try that again. B triple prime AC is this angle. And it's equal to the measure angle BAC. And so AB triple prime maps to AB. And again, they're putting rays up there, and I don't know why. Those should be sides. Side AB maps to side AB. AB triple prime to AB. If, however, AB triple prime, not the ray, the side, coincides with AB, side AB, we can be certain that B triple prime actually maps to B. We can't, why? So it says, if actually maps to B. How do we know if that actually happens? If, however, that coincides, can we be certain that that does? And the answer is we can, because not only are we certain that the rays coincide, but also our assumption that AB is congruent to AB triple prime, or equal. So our assumption began as AB is equal to A prime B prime, but the translation and rotation have preserved the length known now as AB triple prime. Okay, hopefully that's not too confusing to you. So taken together, these two pieces of information ensure that the reflection over AC brings B triple prime to B. So let me just go back and clear that up. Notice the name of this triangle. It's A prime, B prime, C prime. When I slid this over to A, right here, A prime became A. B prime became B double prime. And, oops, C prime became C double prime. See that? And then when we rotated it, the C double prime is going to become C. And on the next step, the rotation B double prime is going to become B triple prime. See that? and C double prime became C because it's sharing the vertex of the original triangle. Okay, hopefully that makes sense to you. Every time you make a move and the congruent part is not shared, the name gets changed to another prime. Another way to visually confirm this is to draw the marks of the blank construction for AC. So what are we going to draw the marks for? Okay, so what do we have to construct? How are we going to confirm this? How do we know that something is going to reflect across? And that is by using a perpendicular bisector. Of AC. So if we constructed a perpendicular bisector of BC, then we'd see that it would go through B and B triple prime. Write the transformation used to correctly notate the congruence, the composition of transformations that take A prime, B prime, C prime, congruent to triangle ABC. So what makes those two triangles congruent? Okay, so F. So now we're talking the names of our functions. So if we go back up, F is right here. They're calling it a function F, triangle A prime, B prime, C prime equals triangle ABC. Okay, so F, the first thing that we did was a translation. Okay, let me go back. So it was this translation. So we went from here to here. Let's get this out of the way. Okay, translation. Then we did this thing right here, which is right here. And that was a rotation. Now we're just writing down what we have just done. And then finally, this getting reflected across AC. H was a reflection. Okay. We have now shown a sequence of rigid motions that takes triangle A prime, B prime, C prime to triangle ABC with the use of just 3 criteria from each triangle, 2 sides and an included angle. There it is, they finally said it, included angle. Given any 2 distinct triangles, we could perform a similar proof. There is another situation where the triangles are not distinct, where a modified proof is needed to show that the triangles map onto each other. Examine these below. Note that when using the side angle side triangle congruence criteria as a reason in a proof, you need only state the congruence and SAS. Okay, page 4, example. What if we had the SAS criteria for 2 triangles that were not distinct? Consider the following 2 cases. How would the transformations needed to demonstrate congruence change? Okay, so here's one case. Shared side. Transformation needed. So now these triangles are already touching. So A is being shared, C is being shared, and side AC is being shared. What do I need to do to map A, B prime, B triple prime, C onto B? What transformation is needed? That's all it's asking. And obviously it would be a reflection across AC. So you just need to say reflection. Okay. And then shared vertex. Well, here, the vertex is already shared. I need to rotate this around so that C double prime ends up on C. So this has to go over here, and then it would look like this, and then that. So a rotation followed by a reflection. Okay. Exercise. So now it's your turn. You're given triangles with a pair of corresponding sides of equal length and a pair of included angles of equal measure. So here they are. So this side is congruent to this side. The side with these two marks is congruent to this side with these two marks. And this angle is congruent to this angle. The angle is included in the sides on both. So that is SAS. So it says sketch and label 3 phases of the sequence of rigid motion that prove 2 triangles are congruent. Okay. So here's what I'm going to do. Let's see. I'm going to, see, I can do this with the program. Unfortunately, you can't. So if I bring this here, let's say I set that right there, okay? And then what I could do is just get rid of that, copy the whole thing. So if I copy this, and put it in here. Okay, so there would be my sketch. What is the first thing that we have to do? Well, we don't have to do anything. Well, it's easier to do the transformation first. So I'm going to say that. So let's do a transformation. So you write transformation. And what transformation we're going to do is we're going to draw a vector from our congruent angle to our other angle that it's congruent to, like so. So the angles that are marked. So there is the transformation we're going to do first. This will slide this vertex over to here. Once we do that, what's it going to look like? Well, and again, this is new because if I pause, it messes up the video. So let me just do this without pausing. I'm going to copy again. And I'm going to copy this piece like so. And I'm going to move it down here. Okay, and I'm just going to shrink that down a little bit. It's not going to be to scale, just so you know. And then I'm going to copy this. And I'm going to move it so that it is now, let's see how I can do this. Well, let me see if it'll pause. Okay, so here it is. I copied it in. It's smaller, but I had to make it fit. So now we have this triangle and this triangle moved over. So that is it. So what do we have to do in this step? We have to rotate. That's a rotation. Okay, and what would it look like after we rotated it? Well, here we go. Bring this over. And here is what it would look like after the rotation. And at this point, we need to reflect. So we did the transformation, we did the rotation, and now we're going to do a reflection across this side. Okay, so that sums up what we were required to do. Translate over, rotate so that one side is shared, and reflect across that side, and the third angle will land on top of the third prime angle, or vice versa. Okay, page 5 brings us to a few more examples. Remember, examples are supposed to be done and then you try them after. So pause this video, see if you can do these, and then come back and we'll check. All right, so assume that you paused, here we go. Justify whether the triangles meet the SAS congruence criteria. Explicitly state which pairs of sides or angles are congruent and why. If the triangles do meet the SAS congruence criteria, describe the rigid motion or motions that would map one triangle onto the other. So number 2 says, given the measure of angle LNM, marked right here, is congruent to the triangle or the angle measure LNO. So in diagrams, they don't always give you the givens marked. So the first thing you should always do is label your diagram with the givens. They've done that for us here. And they've also said side MN equals ON. MN, ON, one mark, one mark. So what we start with is the measure of angle LNM equals the measure of angle LNO. Reason given. So this is statement and this is reason. And then we also say MN equals ON. That is also a given. Okay, so we have a side congruent to a side. We have an angle congruent to an angle. But what else do we know just by looking at this? Well, we have a shared side. So if I have a side, LN, well, it's obviously equal to itself because it's the same thing. So this side right here is equal to itself. And the reason for that is the reflexive property. So now we have an angle, a side, and another, or no, that's a side. So we have a side, angle, side. The angle is in between the two sides, so that is SAS, okay? So now we can finally say that triangle LMN, or actually we should always use the name that it said right here. Do triangle LNM and LNO meet the SAS criteria? So now we can say triangle LNM is congruent to triangle LNO. And the reason is SAS. So does it meet the criteria? The answer is yes. Okay, so let me get that. Oh, pen's acting all wacky. What's going on? Okay, delete that. Move this up. So the triangles map onto one another with a reflection over Ln. So that's what it said up here with the congruent criteria. Describe the rigid motions that would map one triangle onto the other. So since these two are touching, then we would then reflect one triangle over side Ln onto the other. Okay. All right, number 3. So first thing I'm going to do is I'm going to draw my little table. Like so. Okay. And then let's switch back to pen. Let's use green this time. Okay, so now it says, given the measure of angle HGI, which is right here, and they labeled it for us, equals the measure of angle GIG, JIG, it's marked. HG equals JI. They marked them as congruent. So the first thing I do is mark my givens, the measure of angle HGI equals the measure of angle JIG. Do a jig. Given. Okay, that is a given. All right. My pen's acting up. Anywho, there's the first given. The other one is HG equals Ji, given. Okay, there's our two givens. Then we can say Gi is congruent to itself. Why? Reflexive property. Okay, so then I'm going to go up here. What happened here? We know that two angles are congruent. What happened here? We know that two sides are congruent. What happened here? We know that two sides are congruent. And the angle, so they're congruent to each other. So I should have marked that on the last one as well. So let me go up and do that. I should put congruent marks there. It's congruent to itself. Okay, so we have an angle that's included in between the two sides. So it's a given, it's an included angle. So we have, now we can say triangle HGI and always name it in the order of the problem. HGI equals, or is congruent to, I should say, triangle jig. Okay, and the reason, SAS. Okay, and then finally, we're going to state what is going to come next. So how can I move this triangle onto this one? Okay, well, we can't reflect it because then it would flip over and it would be over here like so. And so that's not right. So there is one way. If we put a dot right in the center there, then this is what we would do. The triangle maps onto one another with a 180-degree rotation about the midpoint of diagonal GI. So we'd find the midpoint, rotate this triangle, and it would land right on top of the other. 180-degree rotation. So it could go clockwise or counterclockwise and end up at the same place. So number 4 now says, is it true that we could also have proved triangle HGI, and triangle JIG meet the SAS criteria if we had been given that triangle, that angle HGI? So now they're asking if we could have done this if we were told that angle HGI equals JIG, which is here and here. Okay. And HG equals JI. Okay, so now they're saying, could we have proved this if we were given this was equal to this instead of these? So these are not there. And so now we have, let me erase this. Okay, so my pen, I don't know why it's doing that. Okay, so if we know HGI, so we have this angle here and these sides. And then we know these are congruent because of the reflexive property, but now we have, so if I redrew this triangle, let's just bring this out. Here's G, here's J, and here is I. Okay, so now they're saying, could we have proved this if we knew that this angle and this, or this side and this angle from the triangle? Could we or could we not? There is something else in this diagram, this square here. What does that square mean? It's a right angle, yes. And this is called a leg. If you remember from 8th grade, this is you're going back a couple of years, but that is called a leg. And what is the side opposite a right triangle called? It is a, oops, didn't mean to do that. It is a hypotenuse. This is the hypotenuse. and this is a leg over here. So that is the hypotenuse leg theorem. Okay, so let me bring this in. It's a lengthy answer. So we would say, yes, it is true. Whenever angles are equal, they can also be described as congruent, since rigid motions preserve angle measures. For two angles of equal measure, there always exists a sequence of rigid motions that will carry one onto the other. Additionally, since rigid motions preserve distance for two segments of equal length, there always exists a sequence of rigid motions that carries onto them, that carries one onto the other. So what they're saying here is, given this angle and this side, that's angle, angle, side. But there's also the hypotenuse leg theorem because these are reflexive, but that was not a given. So I guess this way would be better. Okay, does that make sense? Hope so. Okay, page 6 brings us to the end of lesson 22. Go to your problem set.